Hey everyone, and welcome to Hafi Sleep. Whether you're here to unwind after a long day, to drift off into a peaceful rest, or simply to explore the wonders of the universe from the comfort of your own mind, I'm so glad you found your way here. Before we begin our journey to the moon tonight, I have a small request. If the stories and sounds you find here help you relax or spark your curiosity, please consider subscribing to the channel. It truly helps us grow and create more content for you. And if you're enjoying what you hear, giving the video a like is a wonderful way to let us know. I also love hearing from this incredible community. It's amazing to think that we're all sharing this moment together from all corners of the world. So, if you feel like it, drop a comment below and tell me where you're watching from and what time it is for you. Are you cozying down for the night? Or is your day just beginning? It's always fascinating to see just how far and wide this community stretches. Now, find a comfortable spot, close your eyes if you'd like, and let your mind drift. Tonight, we're going to answer a question as old as humanity itself, a story of cosmic violence, incredible chance, and the silent guardian in our sky. Let's begin. Have you ever just stopped and looked up? On a clear night, when the world is quiet and the sky is a deep velvety black, there it is. That familiar, gentle face, glowing with a soft, cool light. The moon. It's been our constant companion, our silent guardian in the sky for as long as there has been an us to look up at it. We've written poems about it, sung songs to it, howled at it, and pointed our first trembling rockets towards its dusty surface. It's so there, so permanent, so obvious. But have you ever, in a quiet moment between those songs and poems, stopped to wonder, why? I don't just mean what it's made of or how it moves around us. I mean, why does it exist at all? What incredible, ancient, violent story of cosmic chance led to this beautiful cratered pearl being strung up in our sky, lighting our way through the eons? That is a story. It's the greatest story ever told, and it begins not with a whisper, but with a cataclysm of almost unimaginable violence. So get comfortable. Let's take a journey back in time, 4.5 billion years, to witness the birth of our moon. Picture the early solar system. It's not the neat, orderly clockwork of planets spinning around the sun that we know today. Oh no, it's a chaotic, terrifying, and spectacularly messy construction zone. The sun is young and fierce, blazing at the center of a swirling, spinning disk of dust and gas and rock. Within this disk, tiny particles are bumping into each other, sticking together slowly gathering themselves into larger and larger clumps. This process is called accretion, and it's how all the planets began. Think of it like a celestial snowball fight on an epic scale. Little snowballs of rock and metal collide and form bigger snowballs, which collide to form even bigger ones. These growing bodies are called planetesimals, the building blocks of planets. In the orbit that would one day become Earth's, these planetesimals were busy. They were colliding, merging, and steadily building a young planet. This infant Earth, though, was a hellish place. It was a molten sphere, constantly being pummeled by these leftover planetesimals. Each impact released tremendous energy, keeping the entire surface a churning, boiling ocean of magma. There was no crust, no solid ground, no atmosphere, just heat, violence, and chaos. And it was into this inferno that our story's main character makes its grand and, frankly, disastrous entrance. Scientists call this object Theia. Theia was another protoplanet about the size of Mars. That's a big boy. It had been forming in its own orbit around the Sun, an orbit that, tragically, was on a direct collision course with our young Earth. The mathematics of gravity are unforgiving. Once two massive objects are caught in each other's gravitational pull, a collision isn't just likely, it's inevitable. So Theia sped through the primordial darkness, a silent bullet aimed directly at the heart of the newborn Earth. The impact, when it came, was something beyond comprehension. It wasn't a glancing blow. It was a direct hit, a head-on collision of apocalyptic proportions. The energy released was so immense that it dwarfs the combined power of every nuclear weapon ever built by humanity, multiplied by 1,000,000. If you could have been there, watching from a safe distance, the sight would have been both terrifying and awe-inspiring. Theia didn't just crash into Earth, it was utterly annihilated, and it very nearly destroyed Earth in the process. The force of the impact was so great that Theia's core, a dense ball of iron and nickel, plunged straight down and sank into the core of the young Earth, merging with it. Meanwhile, the outer layers of both planets, the mantles made of rock, were completely vaporized, not melted, not shattered, but turned into a superheated cloud of vaporized rock, a vast swirling plume of incandescent gas and debris that expanded outwards from the point of impact. This material, a mixture of what was once Theia's mantle and a significant portion of Earth's own mantle, was thrown into orbit around the ruined Earth. In an instant, our planet was transformed. It was left spinning wildly, its day shortened to just a few hours, its surface a deeper, more global ocean of magma than ever before, and it was now encircled by a torus of destruction, a ring of glowing, vaporized rock, like the rings of Saturn, but made of pure fire and chaos. This ring, this aftermath of the most violent event in our planet's history, was the raw material. This was the stuff from which the moon would be forged. So, let's just pause for a second and really soak in that image. Our entire planet, the world we know with its oceans and continents and mountains, was just gone, replaced by this spinning, furious ball of molten rock, wearing a crown of its own destruction. It's a scene of pure, unimaginable chaos. But as with so many things in the universe, from chaos comes order, from destruction, creation. And that's exactly what happened next. All that vaporized rock, that superheated cloud now encircling the Earth, couldn't just stay as a cloud. It had to cool down. And as it cooled, the gas began to condense. Think of it like your breath on a cold window. You breathe out, which is warm and moist, and it hits the cold glass and instantly turns into tiny droplets of water. Well, on a cosmic scale, that's what started happening in that ring of fire. The vaporized rock began to condense into trillions upon trillions of tiny droplets of molten rock. It went from a gas to a liquid, forming a seething, swirling disk of liquid rock droplets, all orbiting the Earth. It was a ring of rain, but a rain made of liquid magma, and just like water droplets in a cloud, they started to bump into each other. Now, this is where the magic of gravity and simple physics really takes the stage. When two of these little blobs of molten rock bumped into each other in the void of space, they didn't bounce off or explode, because they were both liquid, and they were both moving in the same general direction around the Earth. They just merged. They stuck together. It's like when two drops of water on a window pane get close enough, they suddenly snap together to form one bigger drop. This process is called accretion, which is just a fancy science word for sticking together to make something bigger. And it's incredibly efficient. So, You start with trillions of tiny droplets. They merge into billions of marble-sized blobs. Those marble-sized blobs merge into millions of rock-sized pieces, and those, in turn, merge into thousands of boulder-sized chunks. It's a snowball effect, but with liquid rock. And in any system like this, there's always one snowball that gets a little head start, that by random chance ends up being slightly bigger than the others. And that slight advantage is everything. Because the bigger it is, the stronger its gravitational pull becomes. So it starts to attract more material towards itself, growing faster than its neighbors. This is the runaway growth phase. It's like being the most popular kid at a party. Everyone wants to be near you, and your group just gets bigger and bigger. Very quickly, in maybe just a few hundred years, this one object grew to dominate the entire ring. It swept up almost all the available material, clearing its orbit and becoming the single largest object in the sky besides Earth itself. This right here is the moment of the moon's birth, not from a gentle gathering of space dust, but from a furious, rapid-fire gathering of a planet's own remains. This new object, our brand new moon, is what scientists call a proto-moon, meaning it was the moon in its earliest, most raw form. And what a sight it must have been. It was much, much closer to Earth than it is today, perhaps only 15,000 to 20,000 miles away, compared to the 240,000 miles it is now. That is close. If you were standing on the hellish surface of the young Earth, the moon wouldn't be a distant, serene disk. It would dominate the entire sky, appearing 15 to 20 times larger than the sun. It would be an overwhelming, terrifying presence. And it wouldn't be the cool, gray color we know. No, it was fresh from the furnace. The entire surface of this proto-moon was a glowing, red-hot ocean of magma. It was a second sun in the sky, but one of pure, liquid rock, radiating a blistering heat. The Earth and its new moon were like two twins born of fire, locked in a close, dizzying dance, with the Earth spinning so fast that a day was only a few hours long. The sky would have been a breathtaking and horrifying spectacle of a gigantic, boiling red orb racing across a sky lit by a young, fierce sun. But nothing that hot can stay hot forever, especially not in the cold vacuum of space. Without an atmosphere to act like a blanket and trap the heat, the moon's surface began to cool rapidly. And as it cooled, it began to change, to settle, to become a proper world. The same processes that had happened on Earth were now happening on the moon, just on a smaller scale. The global magma ocean began to solidify, but it didn't solidify all at once, and it didn't solidify into a uniform lump. This is where we get the moon's internal structure. Think of a pot of really rich stew that you put in the fridge. As it cools, the fat rises to the top and solidifies into a layer, while the heavier meat and vegetables sink to the bottom. The moon's magma ocean did something similar, a process called differentiation. The heaviest materials, like iron and nickel, despite there not being a huge amount of them, still sank towards the center, forming a very small, dense core. This core is only about 500 kilometers across, which is tiny when you consider the whole moon is about 3,500 kilometers wide. It's like a tiny pebble at the heart of a large fruit. Above that core, the bulk of the moon, the mantle, solidified from minerals that are denser than the ones right at the top. These are minerals like olivine and pyroxene, which are common in volcanic rocks on Earth too. Now, the last stuff to crystallize and solidify was the lightest material. Imagine that magma ocean as a fizzy soda. The last things to settle are the lightest bubbles. In the moon's case, These were minerals called plagioclase feldspar. These crystals were less dense than the still liquid magma, so they didn't sink. They floated. They accumulated at the surface, forming a scum, a crust of bright, relatively light rock all over the moon. This original crust is what we see today as the bright, heavily cratered highlands of the moon. It's ancient, it's battered, and it's basically a foam of feldspar that floated to the top of the magma ocean billions of years ago. But the story of the moon's surface wasn't over yet. Its interior was still hot, heated by the leftover energy from its violent formation and by the decay of radioactive elements. And for more than 1 billion years after its crust formed, that heat needed to escape. Occasionally, the heat would build up enough, or a giant asteroid impact would crack the crust, and molten rock from the mantle would come flooding out. This wasn't like the violent, explosive volcanoes we have on Earth. Because the moon has no water or gases in its magma, the eruptions were calm, oozing flows of basaltic lava, very runny, very dark lava. These immense floods of lava filled in the giant low-lying impact basins, the giant holes left by asteroids, and then cooled into smooth, dark, solid plains. When early astronomers looked up and saw these dark patches, they thought they were oceans. So they called them Maria, which is Latin for seas. And that's what we still call them today. So, the face of the man in the moon is really a storybook. The bright areas are the original ancient crust, the highlands, pockmarked with craters that tell the history of billions of years of asteroid impacts. The dark areas are the seas, but seas of frozen lava that welled up from the moon's interior long after it formed, smoothing over the scars of the most catastrophic impacts. It's a face of two histories, one of bombardment from the outside, and one of volcanic fire from within. And it all started with a cataclysm of unbelievable violence, a chance encounter that turned two worlds into one, and gave the third a companion that would forever change its destiny. But the story doesn't end with the moon just cooling off and sitting there. Its relationship with Earth is a dynamic, ongoing dance governed by gravity. And that's the thing about this partnership between Earth and Moon. It's never been a static, long-distance relationship. It's a dynamic, intimate, and incredibly energetic dance. They are constantly talking to each other, whispering through the invisible force of gravity, and this conversation has literally shaped the world we live in. The most obvious and beautiful result of this conversation is the ocean's tide. We're so used to it, this rhythmic, twice-daily pulse of the sea, that we hardly think about it. But it's a direct message from the moon, a gravitational love letter sent across 250,000 miles of space, and the ocean is writing the reply in waves. So, how does it work? Let's break it down. Gravity, as we know, is the force of attraction between any two objects that have mass. The more mass, the stronger the pull. The moon, being a pretty massive object, pulls on the Earth, but it doesn't pull on all of the Earth equally. This is the key to the whole thing. The side of the Earth that is facing the moon is about 4,000 miles closer to it than the center of the Earth is. And in the world of gravity, distance is everything. The closer you are, the stronger the pull. So the ocean water on the moon-facing side of Earth gets a stronger yank from the moon's gravity than the solid planet itself does. It's like the moon is gently tugging that water towards itself, just a little bit more than it's tugging the rock beneath it. This creates a bulge, a high tide, on the side of the planet facing the moon. Now, this is where most people's brains understandably go. Okay, one bulge, one high tide. That makes sense. But wait, We have two high tides a day. There's another one on the exact opposite side of the planet, directly away from the moon. How on earth does that work? It seems completely counterintuitive. Is the moon somehow pushing water away over there? The answer is even more fascinating, and it has to do with the nature of the dance itself. You see, the Earth and the moon don't just exist near each other. They are locked in a mutual orbit. They're both spinning around a common center of gravity, a point called the barycenter. Now, because the Earth is so much more massive than the moon, about 81 times more massive, this barycenter isn't out in space somewhere between them. It's actually located inside the Earth, about 1,000 miles below the surface, so still within our planet's mantle. So, from a certain point of view, the Earth is doing a very small, lopsided wobble around this point, while the moon makes its much wider orbit. This wobbling motion creates a centrifugal force. You know that feeling when you're in a car that takes a sharp turn and you feel pushed to the outside of the curve? That's centrifugal force. Well, the Earth is constantly turning around this internal point, and everything on Earth experiences a tiny bit of that outward push. But here's the clever part. This centrifugal force is strongest on the side of the Earth that is farthest from the moon, because that's the point on the planet that is on the very outside of this wobble. The solid Earth feels this force, but it's rigid and holds its shape. The ocean water, however, is fluid and free to move. So, on the far side, this centrifugal force actually flings the water away from the moon, creating a second bulge. So, you have two bulges, one where the moon's gravity is pulling water towards it, and one on the opposite side where the wobble of the Earth is flinging water away from it. Now, imagine the Earth spinning merrily on its axis once every 24 hours. As it spins, any given point on the coastline will rotate through both of these bulges. You sail into the first bulge. That's a high tide. You spin out of it, the water level drops. That's a low tide. You keep spinning and sail into the second bulge on the opposite side. That's your second high tide. And then you spin out of that one, and you're back to low tide. This is why, in most places on Earth, you get two high tides and two low tides every lunar day. And a lunar day is why we say it takes 24 hours and 50 minutes. A solar day is 24 hours, the time it takes for a point on Earth to rotate to face the sun again. But in that time, the moon has also moved a little further along in its orbit around Earth. So, for a point on Earth to catch up and face the moon again, it has to rotate just a little bit more, about another 50 minutes worth. So the tidal cycle is 24 hours and 50 minutes. The tides are late by about 50 minutes each day, following the moon, not the sun. But the sun isn't just a bystander in this celestial dance. Oh no, the sun has its own gravitational pull, and it creates its own tidal bulges on Earth. But because the sun is so phenomenally far away, about 93 million miles compared to the moon's 240,000, its tidal effect is only about half as strong as the moon's, even though the sun is so much bigger. The strength of the tide-generating force depends incredibly strongly on distance. So the sun's tides are like a quieter background rhythm, while the moon's are the powerful dominant beat. Sometimes these two rhythms sync up. This happens twice a month, at the new moon and the full moon. At these times, the sun, earth, and moon are all in a straight line. At a new moon, the moon is between the earth and sun. At a full moon, the earth is between the moon and sun. In both cases, the sun's tidal bulge and the moon's tidal bulge line up perfectly. They reinforce each other. The sun's gravity gives the moon's gravity a little boost. This makes the high tides even higher and the low tides even lower. We call these the spring tides. Now, the name has nothing to do with the season. It comes from the Old English word springen, meaning to leap up. So, spring tides are when the tide leaps up extra high. Then, 2 weeks later, the rhythms are out of sync. This happens during the first and third quarter moons. Now, the sun, earth, and moon form a right angle. The moon's tidal bulge and the sun's tidal bulge are now pulling at cross purposes. The sun's bulge is actually pulling water away from the moon's bulge, trying to cancel it out. The result is a much more modest tide. The high tides aren't very high, and the low tides aren't very low. These are called neap tides, from an Old English word meaning lacking power. So we have this beautiful, predictable twice-monthly cycle. Powerful spring tides, then a week later, weaker neap tides, then powerful spring tides again. It's the universe's own metronome. This tidal interaction is a constant, rhythmic energy exchange. And this, right here, is the real magic of the whole thing. This isn't just a one-way pull. It's a constant flowing river of energy, moving from one partner to the other in this cosmic dance. Think of it like a spinning ice skater. When a skater pulls their arms in, they spin faster. When they throw their arms out, they slow down. Now imagine the earth is the skater's body, and the oceans are the skater's arms. The moon's gravity is like a coach, constantly encouraging those arms to stretch out just a little bit further. And just like the skater, when those arms are out, the whole body spins a little slower. That's tidal friction in a nutshell. It's the gentle, relentless pressure of all that moving water, all that sloshing and swirling across the basins and around the continents, dragging against the seafloor. It's like a trillion tiny brakes being applied to the spinning earth, all at once, all the time. Now, a brake that slows something down is stealing its energy of motion, what scientists call kinetic energy. The earth is losing that spinning energy, bit by tiny bit, day by day, century by century. And the result is that our planet's rotation is gradually slowing down. The day is getting longer. It's happening so slowly that you or I or 100 generations of our ancestors would never notice it. We're talking about a change of about 1.5 milliseconds. That's 1.5 thousandths of a single second every century. But give that process a few 100 million years, and those milliseconds add up to something truly staggering. Let's hop in our imaginary time machine again and go back, say, 400 million years. This is the Devonian period on Earth. Life has finally begun its great march onto the land. The first primitive plants are forming forests. The first insects are scurrying in the undergrowth, and funny-looking fish are starting to experiment with crude lungs in the water. If you could stand on one of those ancient shores and look up, the sky would be utterly mind-blowing. The moon would be gigantic, looming about 10% larger in the sky than it does today. But the real shock would be the passage of time itself. The Earth is spinning much, much faster. A day, one full rotation of the planet, is only about 22 hours long. And because the Earth is whipping around the sun in the same amount of time, a year is still a year. That means there are more of these shorter days crammed into a single trip around the sun. A year back then wasn't 365 days long. It was more than 400 days long. We know this for a fact, not from guesswork, but from nature's own time capsules, fossils. Certain corals from that era grow in a very specific way. They lay down a tiny, microscopic layer of growth every single day, and these daily bands are grouped into larger yearly bands, much like tree rings. By counting these incredibly fine daily lines within a yearly band, paleontologists have literally been able to count the number of days in a year for creatures that lived hundreds of millions of years ago. It's one of the most elegant and beautiful pieces of detective work in all of science, and it confirms our planet's gradual slowdown. But here's the crucial part, the part that ties this whole beautiful loop together, the law of conservation of energy. Energy cannot be created or destroyed. It can only be transferred or changed from one form to another. So, if the Earth is losing all this rotational energy, where is it going? It can't just vanish. It has to go somewhere. And it does. It's being packaged up and delivered via the gravitational link of the tides to the moon. This energy transfer is like giving the moon a constant, gentle push. And what happens when you push something that's in orbit? You push it into a higher orbit. It's like spinning a ball on a string around your head. If you give the ball more energy, it will fly outwards, to a wider circle. That's exactly what's happening. The moon is slowly spiraling away from us. Right now, it's moving away at a rate of about 3.8 centimeters per year. That's roughly the same speed your fingernails grow. It's not much, but it's relentless. Over the course of human history, it's added up. When the dinosaurs went extinct 65 million years ago, the moon was about 1,500 miles closer. When those first ancient corals were laying down their daily bands 400 million years ago, it was thousands of miles closer still. And right after the colossal impact that formed it, it was practically next door. Its gravitational pull so immense that it must have created titanic, global tides in Earth's magma ocean that would make our highest waves look like tiny ripples in a bathtub. This dance is a true two-way street. While we're busy stretching our oceans towards the moon is feeling Earth's gravitational pull too. Our planet's gravity is much stronger, and it creates tides on the moon just as the moon creates tides on Earth. But the moon is a very different dance partner. It has no global ocean to slosh around. So instead of moving water, Earth's gravity flexes the solid rock of the moon itself. It creates a solid body tide, a subtle rhythmic bulging of the lunar crust. Imagine gently squeezing a rubber ball over and over again. It flexes and heats up a little bit from the friction. Billions of years ago, when the moon was much closer and hotter inside, this constant gravitational kneading from Earth generated significant internal heat, adding to the warmth from its violent birth and helping to power the vast volcanic eruptions that created the Dark Maria. It kept the moon's interior churning for longer than it otherwise would have. But the moon, being so much smaller, lost its internal heat much faster than Earth. Its engine cooled. The volcanic fires died out. The mantle solidified. Today, this tidal flexing is much weaker, but it hasn't stopped completely. The moon still bulges towards Earth by several centimeters each month. This flexing, combined with the slow, relentless cooling and contracting of its interior, imagine it like a giant rock slowly shrinking and cracking, causes the lunar surface to shudder. We call these moonquakes. Some of them are surprisingly powerful and can last much longer than earthquakes because the moon's dry, rigid structure doesn't dampen the vibrations like Earth's watery, fractured crust does. So, while it may look silent and dead to us, our companion is still subtly active, still feeling the pull of its partner, still whispering back in the only way it can, through the faint, deep tremors in its stone. It's a relationship forged in fire, maintained by gravity, and expressed in the slow, stately, billion-year-long rhythm of the tide. So we've seen how the moon gives us our tides and gently taps the brakes on our spin. But its greatest gift to us, the one that might be the most important of all, is something far more subtle, yet utterly profound: stability. Think of our planet not just as a spinning ball, but as a spinning top. When a top is perfectly upright and spinning fast, it's stable. It hums along smoothly. But if it gets a little nudge, if it develops a wobble, that wobble can start to grow. The top might begin to precess, meaning its axis starts to slowly circle around. And if the wobble gets bad enough, the whole thing can become chaotic, lurching wildly until it finally tumbles over completely. Now, our Earth is a magnificent spinning top in the void of space. It doesn't spin straight up and down. It's tilted over at an angle of about 23.5 degrees, and we should be incredibly grateful for that tilt. That tilt is the sole reason we have seasons. As we travel around the sun, the northern hemisphere is tilted towards the sun for part of the year, summer, and tilted away for another part, winter. It's this beautiful, predictable rhythm that governs the growth of crops, the migration of animals, and the very cycle of life on our planet. But here's the thing. Out in space, there are other players in the game. There are other gravitational forces at work, and they'd love nothing more than to give our planetary top a good shove. The biggest bully on the block is Jupiter. Jupiter is a monster. It's so huge that all the other planets in the solar system could fit inside it with room to spare, and its gravity is immense. As Jupiter swings around the sun, its gravitational field reaches out and tugs on our planet. It doesn't tug on the whole Earth evenly, though, because the Earth isn't a perfect sphere. It's slightly fatter around the equator, a bulge created by its own spin. Jupiter's gravity pulls on this bulge, trying to yank the Earth's axis upright or tip it over further. It's a constant, nagging pull, and if left unchecked, it would make the Earth's tilt unstable and chaotic over millions of years. This isn't just a theory. Scientists who build incredibly complex computer models of our solar system have run the experiment. They've created a digital simulation of our planetary system, but they've politely asked the moon to leave. They've removed it from the equation entirely to see what an Earth solo would be like. The results are terrifying. Without our moon's steadying hand, the gravitational tugs from Jupiter, and to a lesser extent Venus, would cause the Earth's tilt to go completely wild. The axis wouldn't be stable at 23.5 degrees. Instead, it would wander chaotically. Over tens of millions of years, it could shift to almost no tilt at all, nearly 0 degrees. And then, later, it could swing radically to the other extreme, tilting so far over that the planet is almost lying on its side, with a tilt of up to 85 degrees. Let's just pause and imagine those two nightmare scenarios. First, a world with no tilt. This would be a planet with no seasons. The sun's path in the sky would be the same every single day of the year. The equator would be perpetually scorching hot, a permanent blistering band of desert. The poles would be perpetually frozen, locked in deep, dark ice ages. The temperate zones in between would have a constant, unending, bland climate. There would be no spring awakening, no summer growth, no autumn harvest, no winter hibernation. The environmental pressure that drives evolution and biodiversity would be drastically reduced. Life might exist, but it would likely be simple, specialized, and utterly different. Now, imagine the opposite extreme, a tilt of 85 degrees. This is almost unimaginable. For part of the year, the North Pole would be pointing almost directly at the sun. The Arctic region would experience 24 hours of daylight for months on end, baking under the relentless sun. The ice caps would melt, The permafrost would vanish, and the land would become a superheated oven. Meanwhile, the equator, which normally gets the most direct sun, would be in twilight, receiving only oblique, weak sunlight, and would actually become a relatively cool region. 6 months later, the situation would reverse. The South Pole would be pointed at the sun, and the North Pole would be plunged into a months-long frigid night of unimaginable cold. The climate wouldn't just be seasonal, it would be violently schizophrenic. The jet streams, ocean currents, and weather patterns would be thrown into utter chaos. The stress on any ecosystem would be immense. It's hard to see how complex, multicellular life, let alone intelligent life, could ever gain a foothold on such a wildly unpredictable roller coaster of a world. The long, stable, multi-million-year periods of climate consistency that allowed life to slowly evolve from single cells in the oceans to the incredible diversity of creatures we see today would simply not exist. This is where our moon earns its title as the guardian of life. It is our gravitational anchor. Its presence, its significant mass orbiting us, provides a stabilizing force. Think of it as a gyroscope for our planet. The moon's gravity acts on Earth's equatorial bulge too, but it does so in a consistent, regular way. It creates a predictable precession, a slow, graceful 26,000-year wobble of Earth's axis, like a spinning top slowly tracing a circle. This steady wobble overwhelms the chaotic random tugs from Jupiter. It keeps the Earth's tilt within a very narrow, very safe range. For the last few billion years, Earth's tilt has only varied by about 2.5 degrees, wobbling gently between about 22.1 and 24.5 degrees. This tiny range of motion is the reason our seasons are so predictable and relatively mild. It's the reason our climate has remained stable on geological timescales. It's the reason ice ages come and go slowly, giving life time to adapt. We can look to our neighboring planets to see what happens without a large moon. Mars is a perfect example. Mars is a fraction of Earth's size and has 2 tiny, lumpy moons, Phobos and Deimos, which are more like captured asteroids than true moons. They are far too small to stabilize Mars. As a result, the Martian tilt swings chaotically over time, from as little as 15 degrees to as much as 45 degrees. This wild variation is thought to have played a major role in the dramatic climate shifts that saw Mars lose its atmosphere and surface water. Venus, meanwhile, has no moon at all, and it spins backwards with a tilt that is completely extreme, though its thick atmosphere and proximity to the sun are its primary issues. So, when you look up at the moon, you're not just looking at a beautiful rock. You're looking at the steady hand that has held our planet's hand for 4 billion years. It quieted the chaos of our infancy. It calmed the furious magma oceans. It has maintained the gentle, predictable rhythm of the seasons. It provided the stable, nurturing cradle in which life could be born, could experiment, could survive mass extinctions, and could eventually evolve a creature curious enough to look back up at its guardian and wonder, why are you there? The moon's existence is not a coincidence. For us, it was a necessity. It is the silent, watchful protector of our world, the unsung hero of our story, and the reason we have a stable, beautiful planet to call home. So the moon gave us time, and it gave us seasons, but its resume of gifts is even longer and more incredible. To truly appreciate it, we have to go back to a time of fire and brimstone, after the moon itself had formed, but when the solar system was still a very dangerous neighborhood. This period, about 4 billion years ago, is known as the Late Heavy Bombardment. It sounds like a bad sci-fi movie, but it was very, very real. After the planets had mostly formed, there was still a tremendous amount of leftover debris, asteroids, comets, planetesimals, zipping around. Something, perhaps the shifting orbits of the giant planets like Jupiter and Saturn, stirred this debris up, sending a rain of destruction hurtling into the inner solar system. For 100 million years or so, Earth and its new companion, the Moon, were under constant siege. Now here's where the Moon becomes our history keeper. Earth is a dynamic, living planet. Plate tectonics constantly recycle its crust, mountains rise and erode, volcanoes spew new rock, wind and water weather the surface, and life itself covers the evidence of its own past. Earth has a terrible memory. It's like a chalkboard that's constantly being erased and rewritten. But the Moon? The Moon is a museum. It's geologically dead. It has no weather, no water, no plate tectonics. Once a crater is formed there, it stays there, essentially forever, unless another impact overwrites it. So, when we look at the Moon, we are looking back in time. Its heavily cratered face, particularly the bright highlands, is the perfect record of that violent period of bombardment. It's a photo album of the solar system's most chaotic chapter. By studying the Moon's craters, we can understand what Earth must have endured. And it was a lot. Earth, being larger and with stronger gravity, would have been hit even more often than the Moon was. It was a truly hellish time, with impacts so large they could have vaporized the oceans and sterilized the planet. Some scientists think life may have begun multiple times, only to be wiped out by these colossal strikes before it finally managed to gain a permanent foothold. But here's a fascinating thought. The Moon, the very same object that was also being pummeled, might have actually been acting as a shield. Its large size and gravitational pull means it has a pretty big cross-section, as scientists say. It's a big target. It's entirely possible that many asteroids and comets that were on a trajectory that could have hit Earth were instead captured by the Moon's gravity and pulled into a collision course with itself. It took one for the team, over and over again. Now it certainly didn't catch them all. The evidence is written all over our planet, even if we can't see the craters anymore. But it might have reduced the frequency of the very largest, most civilization-ending impacts, making the environment just that little bit less hostile for the delicate chemistry of life to get started. And that chemistry brings us to one of the most beautiful and poetic theories about the Moon's role in our existence. We've talked about the tides it creates today. Now, imagine the tides on the early Earth when the Moon was 10 or 15,000 miles closer. They wouldn't have been gentle rises and falls of a few feet. They would have been colossal, monumental. We're talking tidal bores, hundreds, maybe even thousands of feet high, racing across the globe. They would have scoured the coastlines, creating vast, expansive, and, most importantly, shallow tidal pools. These pools are now the starring characters in a brilliant scientific idea. Imagine one of these warm, shallow pools, nestled on a volcanic rock coastline, rich with minerals and the simple chemical compounds that were brewing in the early oceans. The immense tide rushes in, filling the pool with this nutrient-rich soup. Then the tide recedes, leaving the pool isolated under the young sun. The water begins to evaporate, concentrating all those chemicals, making them more likely to bump into each other and react. The sun's ultraviolet light beats down, providing energy to drive these reactions. Then, just as things are getting interesting, the next tidal surge arrives, refreshing the pool with new ingredients, diluting the mixture, and then pulling back to start the cycle all over again. This constant cycle of wetting and drying, of concentration and dilution, of heating and cooling, is a powerful engine for chemistry. In labs, scientists have shown that this very process can help form the building blocks of life, amino acids and nucleotides, the Lego bricks of proteins and DNA. It's possible then that the moon, by creating these unique, dynamic, rhythmic laboratories all across the early Earth, provided the perfect crucible for life to begin. It didn't just stabilize the environment for life, it might have literally stirred the pot. The moon's influence didn't stop with the origin of life. It extended right into the development of human civilization. Before electricity, the night was a time of profound darkness. But the moon changed that. It gave us the night light. The light of the full moon is utterly different from sunlight. It's softer, dimmer, silvery, and mystical. It casts long, dramatic shadows and transforms the familiar world into something mysterious and new. This light was incredibly practical for our ancestors. It allowed for extended hunting trips, for travel between villages after sundown, for social gatherings and storytelling under its glow. It extended the day, but it did more than that. It captured our imagination. It became woven into the very fabric of our culture. It features in our oldest myths and legends: a god, a goddess, a trickster, a guardian. It's a symbol of romance, of madness, lunacy from Luna, of the subconscious, of constant change within a cycle of permanence. It's been the muse for countless poets, artists, and musicians throughout history. This lunar light is also a fundamental clock for the natural world. Nocturnal animals rely on it to hunt and navigate. Many marine animals, like the great coral reefs, use the phase of the moon to coordinate their mass spawning events, all releasing their eggs and sperm into the water at the same time to maximize the chance of fertilization. And for us, its most enduring practical gift was timekeeping. The moon's cycle is a perfect visible calendar in the sky. It takes about 29.5 days to go from new moon, dark, to full moon, and back to new again. This cycle, a lunar month or synodic month, was one of humanity's first ways of measuring time that was longer than a day but shorter than a year. It was essential for early agriculture, for knowing when to plant and when to harvest, for organizing religious ceremonies, and for tracking the seasons. The word month itself comes from moon. Our modern calendar may be solar-based, but its roots are deeply lunar. So, from the mightiest tidal wave on a primordial beach, to the gentle light that allows a walk through a forest at midnight, the moon's touch is on everything. It is not just a rock in the sky. It is a co-author of our story, a silent partner in our evolution, and an eternal source of wonder. For thousands and thousands of generations, we had only been able to look up, to wonder, to dream. The moon was a symbol, a mystery, a light in the darkness, but always, always out of reach. That all changed in an instant on a single day, July 20th, 1969. The Apollo program was, on the surface, a product of its time, a fierce competition between two world superpowers, the USA and the USSR, a battle for technological supremacy in the midst of the Cold War. But what it produced transcended all of that. It became a moment not for Americans, but for humanity. When Neil Armstrong's boots sunk into that soft, gray lunar dust, it was a footprint for all of us. It was the moment we became a species that could leave our home planet and step onto another world. It was the greatest adventure in human history, And those 12 astronauts who eventually walked on the moon, they weren't just explorers. They were the ultimate field geologists. And their most precious cargo on the journey home wasn't the astronauts themselves, but the treasures they collected. Over 800 pounds of lunar rocks and soil. You have to understand, before this, every single thing we knew about the moon was from looking through a telescope. We were making educated guesses. These rocks were the hard evidence. They were the ultimate truth, delivered right into our laboratories. And they began to tell a story billions of years old. First, they told us the moon's birthday. How do you date a rock that's been sitting there for billions of years? You use a technique called radiometric dating. It sounds complicated, but the principle is actually quite beautiful. Certain elements are unstable. They decay very slowly and at a very predictable rate into other elements. It's like a built-in natural clock. A common one is potassium-40, which decays into argon-40 by carefully measuring the ratio of how much of the original parent element is left in a rock to how much of the new daughter element has been created. Scientists can calculate exactly how long that clock has been ticking, how long ago that rock solidified. When they did this with the oldest lunar rocks, the clock read about 4.51 billion years. This confirmed that the moon formed incredibly early in the solar system's history, just a sliver of time after Earth itself formed. But the real jackpot, the discovery that solved the greatest lunar mystery of all, came from looking not at rare elements, but at the most common thing imaginable: oxygen. Oxygen atoms aren't all identical. They come in slightly different flavors called isotopes. Think of them as identical twins, but one is ever so slightly heavier than the other because it has an extra neutron or two in its nucleus. Now here's the crucial part. Every planet and asteroid in the solar system has a slightly different ratio of these oxygen isotopes. It's like a galactic fingerprint. Mars has its own ratio. Vesta has its own. When scientists measured the oxygen isotope ratio in the lunar rocks, they held their breath. What would the moon's fingerprint be? The answer was astonishing. It was identical to Earth's. Not similar. Identical. This was the final smoking gun for the giant impact theory. If the moon had formed somewhere else entirely and been captured by Earth's gravity, it would have its own unique oxygen fingerprint. But it doesn't. It shares ours. This proved, beyond a doubt, that the moon was made from the same stuff as Earth. It was born from that colossal collision, from the mantle of Theia and the mantle of the young Earth mixing together in that furious disk of vaporized rock. The rocks brought back by Apollo were the ultimate proof of the story we've been telling, but they kept talking. The rocks from the bright highlands, loaded with white feldspar, told of the global magma ocean that once covered the moon, and how the light crystals floated to the top to form the first crust. The dark, dense rocks from the Maria were basalts, telling of a later time when the moon's interior was still hot enough to erupt lava that flooded the giant basins. And every single rock was covered in microscopic craters called zap pits from constant micrometeorite bombardment, telling the story of a solar system that was, for a long time, a very dangerous shooting gallery. The astronauts didn't just bring things back. They left things there. They left behind sophisticated scientific stations. They planted seismometers, incredibly sensitive devices to listen to the moon's interior. And they heard moonquakes, deep, rumbling shudders that taught us about the moon's internal structure, confirming it has a small, dense core, a thick mantle, and a rigid crust. And perhaps the coolest experiment of all, they left behind mirrors. Not ordinary mirrors, but arrays of corner cube retroreflectors, which are like perfect, permanent bicycle reflectors. To this day, scientists on Earth can fire a powerful laser beam at those mirrors and catch the reflection that comes back. By timing how long that round trip takes, about 2.5 seconds, they can calculate the distance to the moon with absurd precision, down to a few millimeters. This is how we know, with absolute certainty, that the moon is slowly moving away from us at that rate of 1.5 inches per year. It's an ongoing experiment that continues to confirm our theories about the Earth-Moon system. The Apollo missions transformed the moon. It was no longer just a distant object of myth and mystery. It became a real place. A place with geology, with history, a place we have visited. Those rocks are not just museum pieces. They are pages from the diary of our own planet's earliest, most violent years, a diary that Earth itself lost long ago. The moon, our silent companion, had been holding on to the secrets of our shared origin this whole time. And it took a few brave humans making a 250,000-mile journey to finally bring that story home. So, why does the moon exist? It exists because of a catastrophic accident, a chance encounter of two young worlds in the crowded early solar system. It is the child of that violence, born from the ashes of a planet named Theia and the wounded Earth. It is the sculptor of our tides, the regulator of our days, the guardian of our seasons, and the stabilizer of our world. It may have been the midwife to life itself, providing the rhythmic tides that stirred the primordial soup. It has been our first calendar, our nightly lantern, our muse, and our first stepping stone into the cosmic ocean. It is a museum, preserving the history of the solar system on its cratered surface. It is a partner in a slow, graceful dance that has lasted for over 4 billion years. The next time you look up at that familiar, gentle face in the sky, I hope you see more than just a rock. I hope you see the story, a story of incredible violence and incredible beauty, a story of chance and necessity, a story that is inextricably linked with our own. It is not just a rock orbiting our planet. It is a piece of our home, a piece of our past, and perhaps a piece of our future. It is our companion, our moon. And it is there because, in the chaotic construction of our solar system, an impact that nearly ended Earth's story instead gave it a partner, and in doing so, may have made all the difference. Good night, and have a deep sleep.